So the next speaker is Xueshuang Xiang, is with the Xueshuang Laboratory, is the China Academy of Space Technology, and he's going to tell us about deep learning for Helmholtz problems.
Thanks for the introduction, and it's my great pleasure to be here to give this talk. So my name is Xueshuang Xiang. I come from the Xueshuang Laboratory, and today I want to introduce some recent work about using deep learning for the Helmholtz problems. And this is a joint work with my student Wu Yang and my student Zhiming Wang and Professor Yingxiang Xu and Tao Cui. So first, I will introduce our motivation. So as we know, the Helmholtz problem is a well-known PDE, and it comes from the problem from, for example, the acoustics and the elasticity and the electromagnetics. And the problem, the definition is very simple. For example, the equation is Laplace u plus k square u equal to f, but the boundary condition is very special. Here we will facing unbounded boundary condition. In the problem, the k equal to omega over c is the wave number, and the omega is the angular frequency, and here the c is the wave velocity, the velocity when the wave propagates. So there are some key issues for the boundary, the discretization, the solver of this problem. And during the last several decades, there were many literatures about these three issues from the aspects from, for example, the homogeneous problem. Here, in the homogeneous problem, where we have the wave velocity is a constant, and for the heterogeneous problem, and the wave velocity is not a constant, but in practical problems, it's always a piecewise constant. So for the aspect of boundary, our goal is to capture the decay of wave propagation in unbounded domain. And in the aspect of discretization, our goal is to reduce the well-known pollution error and numerical dispersion. And in the aspect of a solver, our goal is to handle the highly indefinite nature of a discrete system. So during the last several years, I spent lots of my time on these topics. And now I come to focus on the problem of how to discretize the Helmholtz problem, especially in a heterogeneous domain. So what is the challenge? So, first of all, as we know, the high-order scheme is very helpful. Either we use the finite element method or spectral element method or finite difference method for discretizing the Helmholtz problem. But it's very hard for heterogeneous media, even for the elliptic interface problem. So despite there were some approach like unfitted finite element method and some recent developments for the elliptic interface problem, but there were also some drawbacks. For the first of all is the condition. So this approach will always make some strict condition on the interface. And the second is they need a carefully design of the finite element space. So so for these two problems, they were due to that we use the finite element method, and the finite element method is based on mesh. So then we want to ask that is, can we instead use a mesh-free scheme like deep rays and the pin? But we also found that a single neural network is very hard to capture the interface influence, because we know that for the interface problem, for example, the derivative of the solution across the interface is not continuous. But if we use only a single neural network, for example, with the activation function like tangent h or a sigmoid, the solution is continuous. So then our goal is combine domain decomposition and deep learning to develop a high-order scheme for the heterogeneous Helmholtz problem. So to achieve this goal, we first want to test how does the performance of combine domain decomposition and deep learning for elliptic interface problems, and then we want to design some efficient or effective neural network for Helmholtz problems, especially high-order neural network problems. And then we want to combine these signatures. We want to combine these signatures for the heterogeneous Helmholtz problem. So then I want to introduce the first one is the deep domain decomposition method. And the idea is very natural. That is, For instance, we take the classical domain decomposition, the Schwarz method, for example. Here we have a problem and divide in omega. So first of all, we divide the omega to two subdomains, omega 1 and omega 2, and some the corresponding subproblems. And the domain decomposition method is that we can solve these two subproblems separable, and at each iteration step, we interchange the information through the interface. So this is the basic idea. And our deep domain decomposition method is that we instead using the neural network, for example, PIN to discretize these two subproblems. And for different subproblems, we may use different neural network. So generally speaking, consider general PDE like this. And first, we divide the domain to several subdomains and define the corresponding subproblem. And then we define a local neural network for each subproblem with the optimization objective, which includes three parts: the inside part, the boundary part, and the interface part. So then we can use domain decomposition for the outer iteration, and at each iteration we solve these optimization problems. And then we have two kinds of iteration: the outer iteration for the domain decomposition and the inner iteration for training. So first we want to test how does our method perform for the model problem, and we consider this simple model problem, and we use PIN to discrete each subproblem. And here we just consider a full connected neural network, and we denote the layers, the number of hidden layers, and we denote the units, the number of units per each layer. So here I also give an example of when we have two subdomains. The table here shows that the relative L2 error and the number of outer iterations for different network architectures for 2 or 4 subdomains. So these results can clearly demonstrate that for the model problem, the number of iterations is independent of the network architecture, is just around 6 or 8, and the L2 error is also acceptable around 10 minus power, but 10 power minus 3. Okay, so then I also I also give the relative L2 error and the number of outer iterations for different overlapping size for 2 or 4 subdomains. So this results also, we can see that the number of iterations and the error decrease with increasing the overlapping size. I also show the convergence rate. So here we can see that for the model problem, the convergence rate is consistent with the theoretical analysis on the continuous PDE by Gander. So these results, we can see that if we instead use deep learning to discrete the subproblem in the domain decomposition method, the results is consistent. The results are consistent when we use finite element or finite difference method to discrete the subproblem. So then we want to show that how does our method perform for the interface problem. So here I just give a very simple interface problem. Here we so due to the interface, we divide the domain to omega 1 and omega 2, and here the contrast ratio we denoted by alpha. So the results also show that give that our method exhibits competitive performance on the interface problem. For example, when the contrast ratio be 2 or even be 20, okay, so the L2 error is around 10 power minus 3, and the intuition number is also very small. So here we can conjecture that our method may have a very good performance on the interface problem. So next I will introduce applying wave activation for the Helmholtz problem. So the idea is quite simple. For example, for the traditional activation-based neural network, we may use a tangent HX as the activation function, and here we consider that since the applying wave is the basic component of the solution of Helmholtz equation, we just instead use the applying wave function as the activation function. So we conjecture that this activation function may increase the representation ability of the neural network. So at the same time, we also found that if we use the applying wave activation function, we found that if we use one hinternail and here, the output of the neural network is as follows. Here we have the weights Si and omega I, and here omega I is the direction of the applying with E I omega I x. So we obtain these weights by learning a non-convex problem. So from this formulation, we found that PWN our method is a generalization of applying with partition of unity method proposed by Babuska and Malik. So for the PWPM method here, the applying with basis, the Ki is fixed. Okay, so for this method, we just have the parameters Si, and we obtain these parameters by solving a linear system, a convex linear system. So that's very interesting. That is, our method is a generalization of the traditional, of the classical method for the Helmholtz problem. And here, the main difference is that we need to learn the basis, but in the PWPM, the bases are fixed. So now we consider the performance of our method on two cases. The exact solution is a combination of applying waves with or known direction or unknown direction. So for the known direction problem, here we consider the exact solution is a circular wave based on a Bayesian function. And these two tables give the comparison between our method and the traditional activation method TAN and the PWPM. So for the first table, we can see that our method works much better than the traditional activation method for Helmholtz problem. So this can verify that our motivation, that is, the applying wave activation actually can increase the representability. So the second table gives the comparison between our and PWPM, and from this table can see that our method also has competitive performance in the classical PWPM. But here we just considered the KD problem, which means we know the direction of the exact solution. But in practical, we also don't know the direction. For example, for the heterogeneous Helmholtz problem, we cannot expect to accurately predict the directions of the multi-reflection or multi-refraction waves. So for this more practical problem, we construct the exact solution as follows: to be a combination of several of d plane waves, where each plane wave, the direction Ki is randomly selected. So for this problem, the table shows the comparison between our and the PWPM. Here we give four groups, D and units. Here, where D is the exact number of the plane waves in the exact solution, where units denote the basis, denote the number of bases used in PWN. So this table we can see that our method works much better than the PWPM. So from this, we can conclude that our method can learn a group of optimized plane wave bases, and especially for the more practical problems. Okay, so I give a summary and the ongoing work. So for the goal to combine deep domain decomposition and deep learning to solve heterogeneous Helmholtz problems, we propose the deep domain decomposition method for handle the interface problem, and then we design plane wave activation for the Helmholtz problems, and now we are designing a high-order neural network for solving a general PDEs, and then we will combine these techniques for heterogeneous Helmholtz problems. Okay, so thanks.
Xueshuang,
yeah.
Are you there?
Okay. Yeah.
Hey, so there, I think you had some questions already that you answered. Could you tell us just a little bit about that?
Okay. So the cooperation with cutting-edge activation in also includes multiple layers. Well, for the comparison with PWPM, to be fair, we only consider one hidden layer. Since only the one hidden layer, PWM can be seen as a generalization of the classical approach PWPM. So here is my comment.
All right, thank you. And I wanted to ask something. I mean, this is a bit far from what I usually do, so I don't know if this is, this might be a bit of a naive question, but when you're trying to train neural networks to solve some of these problems, can you say a bit about what difference does it make, what kind of data you use? If you train it on data related to solved problems, or if you do some kind of reinforcement learning to see how well the network is doing, and then you use that to make some kind of policy to improve the network? Like, how do these things, how do they affect the performance, and what is best, and so on?
So you mean the comparison with the reinforcement learning, or sorry,
For example, so if you're training, you know, you're solving some, you mentioned solving PDEs, if I'm correct, at some point, right?
Yeah.
The end of your talk, right? So if I'm solving, you know, trying to find an automatic solver for some of these problems, I can imagine very different ways of doing it. One could be I have some other solver that works as a teacher solver, or one is I can just have the network try to do something and then evaluate the solution by solving, you know, the direct problem of seeing how good the solution is, and then coming up with some kind of reinforcement learning strategy to improve the network.
Okay. That's very interesting. So when we do this problem, we use a neural network to discrete the problem just like the pin. You mean?
Yeah, but how? I guess what maybe this is maybe this is too naive a question, but it's not clear. How do you train the network? I guess this is my question.
Okay.
If you could say a few more words about how you train the network.
Yeah. We just use the traditional optimizer like STD or something like this to train the neural network.
But what data do you give it to? You know, what is the data that it's learning, that it's
Okay,
training
we're sampling
on?
the data. We sample the data in the domain. We randomly sample the data in the domain.
I see.
Okay.
We had a we had a suggestion on the chat. If you could just show the loss function again, maybe this would be helpful. You know, if you could share your slides and show the loss function.
Okay, so here is my loss function.
Yeah, the thing you optimize when you're training.
Yeah. So for this part is the inside part, and here is the points, and we for the two domain case, here we give an example. Okay, so this point is I used for training.
Okay. Thanks so much.